Good evening, everyone. Uh, I welcome you all to the second last chapter of this physics series, Structure of Atoms and Nuclei. Yes, we are a little late. Okay, चलिए. Okay, so yes, we have this new chapter, the second last chapter, and also according to this is a very small chapter because a lot of points have been deleted by the board. Okay, you can see more than 50% has been deleted. Right from 15.7 to the end, everything has been deleted. सिर्फ हमको 15.6 तक ध्यान से अच्छे से करना है. Okay, so 15.6, that's Bohr's atomic model. This chapter is kind of very used to everyone, since this chapter we have been studying since 7th standard, I guess. तो हमने ये सारे नाम जो है साइंस में कहीं ना कहीं सुने हुए हैं. तो since 7th 8th standard we know these names. Okay, रुदरफोर्ड हो गया, थॉमसन हो गया, देन नील्स बोर्स हो गया. तो ये सारे नाम हम पढ़ रहे हैं. एंड इन दिस चैप्टर वी आर काइंड ऑफ going to revise it. We are kind of going to fortify this chapter. Okay, इतना ही है. It is already given in this textbook as well. This chapter is not that unraveling कि आपको कुछ नया मिल रहा है या something that you have never learned kind of stuff. मतलब अब तक का जो हमने पढ़ाई किया for 12th standard physics. Okay, so that was pretty much new. Okay, new as in yes, it was a continuation, but it was a continuation from 11th standard or maybe थोड़ा बहुत 10th standard. Okay, so ये सारा continuation तो है ही है. But this chapter, the structure of atoms and nuclei, we have been studying 6th 7th standard. नाम पढ़ रहे, कुछ atom होता है वगैरह वगैरह. So all this we have been doing, and it's just a fortification to whatever we have already done. Okay, and yeah, as I've said that a lot of part has been omitted, so we will be dividing this chapter. Niels Bohr's के आगे का part we'll be doing in the next lecture since there's a time crunch this today. And उसके पहले का जो part है, I guess 15.5 तक, that is atomic spectra, we'll try to complete it till there and remainder part tomorrow. Okay, so it equally divides the chapter, and then we can learn it and understand it in two proper ways. Okay, into proper lectures. Okay, so let's just start and dive into the chapter. Okay, structure of atoms and nuclei.
Chapter 15 Structure of Atoms and Nuclei. Can you recall? What is Dalton's atomic model? Answer. Assumptions of
See, these are direct questions that are given in your textbook on the left top side. Okay, तो वहाँ पे लिखा है, 3-4 क्वेश्चन छपे हुए हैं. What's Dalton's atomic model? Then who's J.J. Thomson? Then after them, who's Rutherford and what did he do? And then finally, who's Niels Bohr and what did he do? Okay, तो ये questions हम बहुत पहले से पढ़ रहे हैं. These are very known questions. This kind of this topic kind of seems that it is coming from our chemistry part. Yes, it is a part of chemistry, but there's a physics perspective, a physics angle given to this chapter for learning this various aspects of physics from this chapter. Okay, बेसिकली एटम्स एंड न्यूक्लियाई आपको पता है केमिस्ट्री में बिलोंग करते हैं, और उसके अंदर के जो इलेक्ट्रॉन्स है, उसके अंदर के जो चार्जेस है, राइट, इलेक्ट्रॉन्स एंड चार्जेस दैट इट हैज, एंड वो जो न्यूक्लियस है उसके अंदर जो पूरा पॉजिटिव चार्ज भरा पड़ा है, ठीक है, उसके अंदर जो न्यूट्रॉन्स है जो उसको वेट देते हैं, प्रोटॉन्स है जो उसको वेट देते हैं, उसको चार्ज देते हैं, उसका पढ़ाई करना है. ओके, ऑल्सो another topic is relevant to this is radioactive decay, but again इसको physics perspective देना is a little difficult. The reason being radioactive decay completely comes under the part of chemistry, but still we will be learning few basics about the radioactive decay. Okay, ज़्यादा नहीं है, बहुत छोटा part है. So all these three four things that we have seen, तो हमको ये पढ़ना है. Okay, so initially see now in this introduction we'll see. Okay,
Of
we'll just
Dalton's atomic
look into these
model,
questions first, then
matter
we'll
is made up of indestructible particles. Atoms of a given element are identical. Atoms can combine with other atoms to form new substances. What are atoms made of?
So this is what
Answer.
Dalton gave the answer, right? That those were the three, 4 points as given by Dalton. That it is made up of atoms. All atoms are identical. Atoms can combine. Atoms cannot break. Okay, atoms can combine, but atoms cannot break. So in simple straightforwardness, you can understand that this is the limitation. This is the first limitation in his first point given by him. Okay, that atoms are indestructible.
Atoms consist of positively charged nucleus which is 10 to the power 5 times smaller than the size of atom and contains 99.9% of its mass and negatively charged electrons. Nucleus itself is made of protons and neutrons.
Neutrons, right?
What
See,
is
मतलब ये
wave
पढ़ा हुआ
particle
है अपन ने
duality?
already.
Answer. Wave
Wave
particle
particle duality
duality
we
of
have
light
learnt in earlier chapter,
electromagnetic radiation.
right?
Light has both particle and
And
wave
wave
like
like nature.
nature. Phenomena such as diffraction and interference of light could be explained by treating light as electromagnetic
Electromagnetic
waves.
waves.
However, the black body radiation or photoelectric effect could not be explained by wave nature of light. This could be accounted or by considering particle nature of light. Thus, both phenomena could be explained only by accepting that light has dual
Dual
behavior.
behavior.
When light interacts with matter, it behaves as a stream of particles called photons. And when light propagates, it behaves as an electromagnetic waves.
Yes, this is what we have learnt
What
already,
are
so I'm not
matter waves?
interfering into it. Okay.
Answer. Concept of de Broglie,
De
that is
Broglie,
matter wave.
right? We have learnt it.
According to de Broglie, every moving particle is associated with a wave of wavelength given by
That wavelength
lambda is
lambda n.
equals to h by p, which is equals to h upon mv. These waves are called matter waves. As
Yes.
v tends to 0, lambda tends to infinity,
Infinity.
and as v tends to infinity, lambda tends
See,
to
1 by
0.
infinity
This
everything turns
implies
to
that
0.
matter waves are associated with material particles only
Only if
if
the
they are moving.
moving, right? अगर बॉडी मूव कर रही है तभी हमको उसका वेवलेंथ मिलेगा, तभी उसका पार्टिकल नेचर हमको पता चलेगा, और else there will be no particle nature, there will be no wave nature. Okay, this is very important. इतने इसमें मैटर वेव्स के इसमें डिब्रॉय ने पिछले चैप्टर में हमको बता दिया था that what are matter waves and what is the concept of matter waves. Okay, and how they are formed and why we as humans do not show the वेव नेचर. क्यों? क्योंकि हमारा वेवलेंथ बहुत 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 छोटा होता है एज कंपेयर टू सम अदर वेव्स दैट वी सी. ओके, लाइट वेव, विजिबल लाइट का वेव जो हमको दिखता है, रेज ऑफ लाइट दिखता है, दोज आर इन द फॉर्म ऑफ वेव्स बिकॉज उनका वेवलेंथ कंपैरेटिवली बहुत बड़ा होता है अपने से, राइट, लाइक ह्यूमन से. सो हमारा पार्टिकल नेचर जो है वो, दैट आर पार्टिकल नेचर इज इजीली सीन, right, and our wave nature is not easily seen. The only reason being we have a very 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 short wavelength. Okay, और वेवलेंथ को अगर कंटिन्यूअस रखना है तो आपका बॉडी कंटिन्यूअस मोशन में होना कंपलसरी जरूरी. यू मस्ट हैव हर्ड दैट लाइट नेवर स्टॉप्स, इट कीप्स मूविंग, इट जस्ट कैन नॉट स्टॉप. दैट्स व्हाई उसका वेव हमको दिखाई देता है या दिखते रहता है. ओके, ओके, चलो, नाउ लेट्स गेट टू द
Introduction.
चैप्टर.
Greek philosophers Lysippus 370 BC and Democritus 460 to 370 BC were the first scientists to propose in the 5th century BC that matter is made up of indivisible parts called atoms.
Right, so see, this is 370 BC, this is 460 BC, Democritus and Lysippus. But the earliest, ठीक है, इससे भी अर्ली एक साइंटिस्ट कह सकते हो या वैज्ञानिक कह सकते हो, जिसको हम हिंदी या मराठी में बोलते हैं, इट इज महर्षि कन्नड़. ओके, so it was Maharshi Kannada in the 6th century BC when he gave the theory of Anu, that is atom. Okay, he was the first person to actually tell the world that everything or every matter is made up of some smaller part which is called as atom, or he called it as anu, right? So he was the first guy. So basically, being Indians, we should all be proud that yes, all the concepts of science, all these great concepts, easy concepts, whatever we call them, have turned up or initially been spoken out by some of the other Indian, but but the West or the Western world has not accepted it, or let's say they have tried to avoid our explanations, rejected our theories, and that's why they have. And before we could propose our theories and propose our greatness that was all present earlier, उन्होंने अपना अपना बड़ा कर दिया कि अपना अपना नाम डाल दिया उसको, इसने ये दिया उसने वो दिया। उसके पहले बहुत कुछ हमने दे चुके थे, ग्रीक फिलोसोफर्स के पहले हम दे चुके थे। कन्नड़, महर्षि कन्नड़ थे, यू मस्ट बी नोइंग इन बायोलॉजी एज वेल। सुश्रुता हैड डन, I guess, a facial surgery, right? Or Charaka and all those various, what do you say, doctors or scientists had discovered lot many things what have been discovered today. Okay, I guess it was gravity which was totally Newton's। gravity का कुछ पास्ट में या इंडियन पास्ट में, इंडियन हिस्ट्री में कहीं पे भी मेंशन नहीं मिला एज फार एज आई नो। ओके, आई एम नॉट श्योर इफ इट इज फाउंड, इफ इट इज फाउंड दैट विल बी फर्दर प्राउड, बट इफ इट इज नॉट, ओके, न्यूटन माइट बी completely given the credit for it। बट बाकी बहुत से जो भी कंसेप्ट है, फिजिक्स हो गया, केमिस्ट्री हो गया, या फिर आपका बायोलॉजी हो गया, एंड एनी अदर ब्रांच ऑफ साइंस विच वाज ऑलरेडी एक्चुअली डन इन इंडिया, तो ये तो अभी अपने ही टेक्स्ट बुक सी। एंड हाउ tragic it is, how ironic it is that in Indian textbooks we find um, the names of other people first। ठीक है, यहाँ पे there could have been a mention of Maharishi Kannada, but they haven't। or maybe even if you see your textbooks in history, they'll always call the great Mughals, and normally the Indian powers like normal Rajputs, or just the Marathas, or just the people from other regions of the country, they would never say ki the great Marathas or the great Rajputs, they'll say great Mughals, the great British। and like this sometimes makes us think कि क्या चल रहा है, but yes, it is what it is। So basically, coming to this physics point of view, that it was Maharishi Kannada who had already told the world that every matter is made up of something smaller which is called as anu or atom। and then obviously similarly, see, it is not like that कि कन्नड़ ने बोला तो उनका इंफॉर्मेशन कहाँ ही तो ग्रीक में जाके पहुंचा, then the Greeks realized, okay, the Greeks realized by themselves that the matter is indestructible, sorry, the matter is destructible and is made up of some smaller particles called as atoms। Yes, they were that smart and good enough to know by themselves, but we Indians had already done that। Okay, so it was, in that period, it was never a race of who's doing it first, it was just ढूंढो। तो Greeks being well connected and well known to the western world, तो उनका theories जल्दी जल्दी उठा लिया जाता है, और Indians को थोड़ा east में होने की वजह से they avoid to accept, or they generally reject our theories। तो ये Lucifer's Democritus तो अच्छी बात है, but always remember Kannada as well। Okay, महर्षि कन्नड़।
Dalton, from 1766 to 1844, gave his atomic theory in early 19th century.
And this part, see, 1700s, 1800s, 1900s, and 16, 17, 18, 19, ठीक है, ये जो 4 centuries हो गए, so these 4 centuries were actually dominated by the western world, as you can see। and their domination was a result of we not being able to perform, or we not being able to come up with the theories, because they were ruling us, they were not allowing us to to do uh, researches and do these practical great experiments। नहीं तो we could have been always been ahead, but हमको नहीं आने दिया, and we were ruled by the Mughals, then by the Britishers। So like those 500 years of Indian history has been really poor. 500 to let's say 600 years of history, and that held us back in this modern world. And those 600 years have been very critical for the rest of the world, where inventions, innovations were on a very high scale. And yeah, those 500 years have taken us back a lot many years. Okay, Shali. So his theory, he gave 3 4 points. So these are the first few points.
According to his theory, matter is made up of indestructible
Same.
particles. Atoms of a given element
This is
are
Dalton's theory.
identical,
Okay.
and atoms can combine with other atoms to form new substances. That atoms were indestructible was shown to be wrong by the experiments of J.J. Thomson,
What is?
1856 to 1940, who discovered electrons in 1887.
So this was
He then
Dalton. Sorry, J.J.
proceeded to
Thomson,
give his
sir.
atomic
J.J.
model.
Thomson. So he got a Nobel Prize for this. And in the last chapter or the previous chapter, we had learned that his son had also got some Nobel Prize. So this was one of the father-son duos who are credited with a Nobel Prize in physics. So you can go back into the previous chapter just for fun and try to recall who it was or which Thomson it was and what was his model. Okay, let's move ahead. सो जे थॉमसन ने बोला कि नहीं, जो आपका एटम है, जो डाल्टन ने बोला कि इंडेस्ट्रक्टिबल पार्ट है एटम, तो जे थॉमसन ने फर्दर एक्सपेरिमेंट्स किए. फर्दर एक्सपेरिमेंट्स करने के बाद उसको पता चला कि नहीं, ऐसा नहीं है. एंड इट्स नॉट that atom is indestructible, but it is destructible and it is made up of various things. And what are those things?
Which had some deficiency and was later
We will
improved
learn
upon by
later.
Ernest Rutherford,
Then it was Ernest
1871 to
Rutherford, then
1937,
Niels
and
Bohr's.
Neil Bohr's, 1885 to 1962. We will discuss these different models in this chapter.
There was also
We have
Goldstein
already
in
studied
between.
about atoms and nuclei in 11th standard in chemistry.
See, as I started with
This
this
chapter
chapter,
will
okay?
enable you to consolidate your concepts in this subject.
Right, what I said was
We will learn
fortify
that
your concept or consolidate your concept. इतना ज़्यादा कुछ excessively नया नहीं पढ़ने वाला. So the thing is, बहुत limited portion है and marks can be scored easily. मतलब कम ही portion है तो आने वाला भी chances उसमें से है. देखो, they have to ask questions from every chapter. If the chapter is there in the portion, there is going to be some or the other question from that chapter. और इसमें है ही 3 4 पॉइंट पढ़ने के लिए. इफ वी हैव 15.1 which is introduction, 15.2 Thompson's model, 15.3 has been omitted, 15.5 and 6, ठीक है, 4, 15.4 5 and 6, that's all. अगर 4 ही पॉइंट या 3 ही पॉइंट पढ़ने हैं अच्छे से, और उसमें भी खाली बोर्स एटॉमिक मॉडल इतना ही इंपॉर्टेंट है, बाकी सब बहुत छोटे छोटे पॉइंट है, या 15.5 दैट इज एटॉमिक स्पेक्ट्रा, दैट माइट बी आस्क्ड फॉर 3 मार्क्स, नॉट मोर देन 2 or 3 मार्क्स, इससे ज़्यादा इसका वेटेज है नहीं. तो इट्स ईजी फॉर यू टू स्टडी दिस चैप्टर एंड कीप इट असाइड कि पढ़ लिया, कुछ भी पूछ लो मेरे को आ जाएगा, एंड आई एम गोइंग टू गेट माई मार्क्स इन दिस चैप्टर, राइट. हाँ, कंसिडरिंग ऑन द टर्म्स ऑफ सीईटी और कंसिडरिंग ऑन द टर्म्स ऑफ जेई, तो ये इतना इंपॉर्टेंट चैप्टर नहीं बनता है. ओके,
that an atom contains a tiny nucleus whose size or radius is about 1 lakh times smaller than the size of an atom. The nucleus contains all the positive charge of the atom and also 99.9% of its mass. In this chapter, we'll also study properties of the nucleus, the forces that keep it intact, its radioactive decay, and about the energy that can be obtained from it.
right. So this is what, again, mostly see all this radioactive decay, as I've told, ये physics का part कम और chemistry का ज़्यादा है. The energy that can be obtained from, yes, when the electrons jump from one orbit to another orbit, or when the atoms break down, or when the atoms combine together, तो ये जो जब प्रोसेसेस होते हैं तो देर इज सम काइंड ऑफ एनर्जी रिलीज्ड. ओके, सो इफ दैट एनर्जी कैन दैट बी एनर्जी रिलीज, कैन दैट एनर्जी बी हार्नेस्ड इनटू समथिंग एल्स एंड यूज्ड अप लेटर, ये सारी चीजें हमको यहाँ पे डिस्कस करनी है, ऐसा चैप्टर में कहा गया है, बट वो भी कम है. ठीक है,
Thomson's atomic model.
a very simple
Thomson's
straightforward
performed
model.
several
आपने
experiments.
एवरीवन मस्ट हैव सीन वाटरमेलन, राइट. तो सर जी का कहना था इट इज काइंड ऑफ अ प्लम पुडिंग या वाटरमेलन बोल दो. तो वो जो रेड पार्ट है दैट इज योर पॉजिटिव चार्ज, और वो जो ब्लैक सीड्स है दैट बिकम्स योर इलेक्ट्रॉन्स, दैट्स इट. This was the simplest way of him putting up the atomic theory. Okay, so he called it plum pudding model as well. Okay, and yeah, a very easy part.
Experiments with glass vacuum tube wherein a voltage was applied between two electrodes inside an evacuated tube. The cathode was seen to emit rays which produced a glow when they stuck the glass behind the anode.
ठीक है,
By
तो
studying
यहाँ से इलेक्ट्रॉन्स निकले तो यहाँ पे एक चमक उठी. There was sparkle, there was a scintillation here. Scintillation is kind of sparkle or a twinkle, you can see, right? Twinkling of light you must have seen. तो पीछे के साइड, एनोड के पीछे के साइड कुछ ट्विंकलिंग दिखा, मतलब there is some change. See, it is everything. Science हो, science, basic science is all about your observation, how keenly you observe. You must have known Sherlock Holmes, right? सबको पता है. उसका ऑब्जर्वेशन ही इतना स्ट्रांग हुआ करता था कि नो प्रूफ वुड, यू नो, नो एविडेंस वुड हाइड फ्रॉम हिज आईज. सो इट वाज दैट स्ट्रांग ऑब्जर्वेशन. सिमिलरली यू हैव टू बी कीन ऑन ऑब्जर्वेशन एंड अंडरस्टैंडिंग कि क्या चल रहा है.
the properties
तो
of
यहाँ
these
पे
rays,
चमक
he
उठी.
concluded that the rays are made up of negatively charged particles which he called electrons. This demonstrated that atoms are not
नॉट
indestructible. They contain electrons which are emitted by the cathode. Thomson proposed his model of an atom in 1903. According to
1903.
this model, an atom is a sphere having a uniform positively
सो
charged
ये जो
in
ऑरेंज
which
कलर, रेड
electrons
कलर
are
दिख रहा है,
embedded. This model is referred to as plum
प्लम
pudding
पुडिंग
model.
मॉडल, राइट? प्लम पुडिंग बोल दो या इसको वाटरमेलन बोल दो, चल जाएगा.
The total positive charge is equal to the total negative charge of electrons in the atom, rendering it electrically neutral.
अकॉर्डिंग टू हिम.
As a
ओके.
whole solid sphere is uniformly positively charged, the positive charge cannot come out and only the negative charge electron, which are small, can be emitted. The model also explained the formation of ions and ionic compound. However, further experiments on structure of atom, which are described below, showed the distribution of charges to be very different than what was proposed in Thomas'
थॉमसन,
model.
थॉमस नहीं, थॉमसन मॉडल में जो भी प्रपोज किया था उसमें बहुत सारे डिफरेंसेस, बहुत सारे चेंजेस हमको देखने मिले, विच वर शोन अप बाय रुदरफोर्ड, विच विल बी लर्निंग नेक्स्ट.
Gelger-Marsden experiment.
So Giger Marsden, actually it should be Marsden experiment, again a very small simple experiment. So this Giger and Marsden were students of Dalton. Okay, were students of Dalton, and they also decided to do some experiments. So obviously every student is, you know, keen on proving the teacher that they are doing it and they are trying to be better than their master, obviously. So they did it, they did some experiments, and they did try to prove whatever Thompson said was not completely false, but yeah, partially false. And they gave their own theories, or they gave their own postulates here.
In order to understand the structure of
Again, this point is completely omitted. Marsden experiment. Remember this. We are just doing it for the sake that continuation rahe. Bas, this is omitted already. I am telling you.
atoms, Rutherford suggested an experiment for scattering of alpha particles by atoms. Alpha particles are helium nuclei and are positively charged, having charge of 2 protons. The experiment was performed by his colleagues Gelger 1882 to 1945 and Marsden 1889 to 1970 between 1908 and 1913. A sketch of the experimental setup is shown in the figure. Alpha particles from a source were collimated, that is, focused into a narrow beam,
See,
and were
collimated
made to
अभी देखो.
fall.
Collimator मतलब क्या है, देखो यहाँ से if you can see, again omitted है, we are just doing it. Okay, so यहाँ से you can see the ray of light and how scattered the ray of light are. How scattered are these? Very scattered, right? Very scattered. But this collimator, what it does, it takes all the particles together and forms a single beam of light like this. So इसको हम बोलते हैं collimator. ठीक है, तो ये एक्सपेरिमेंट में से ये रेज निकल रहे, बट दे आर लाइक काइंड ऑफ कन्वर्जिंग एट दिस पॉइंट. No, I mean they are falling on this point. They have been, you know, crumbled together और उसको एक beam of light की तरह छोड़ रहे हैं. And again, why do you must have heard many a times कि रुदरफोर्ड ने गोल्ड फॉइल लिया या बाकी सब एक्सपेरिमेंट्स में गोल्ड फॉइल लिया. So the reason being gold foil is always used is that it is highly malleable. Okay, you must be aware of the properties of metals, that they are highly malleable and ductile, and gold has highest, one of the highest malleability. Okay, मतलब क्या है कि उसको आप बहुत बारीक से बारीक शीट में आप उसको बना सकते हो. यू कैन मतलब रोटी जितनी पतली वैसे उतनी आपकी, उससे बहुत कई गुना ज्यादा आपका गोल्ड फॉइल पतला हो सकता है. दैट मीन्स यू कैन, I won't say this would be exaggeration, but I can say you can reach to its atomic level. कि इतना आप उसको पतला कर सकते हो. This is exaggeration, I agree, but yeah, इसीलिए वो extra thin हो सकता है. This is the reason it is used. And then easily देखो, if you are performing experiment for learning of atoms, so you should be shooting something directly on the atoms, right? And who's going to give you direct atoms, or very, no, not direct atoms, but at least उसके आजू बाजू, तो it will be your gold foil. ओके, तो ये याद रखो. तो गोल्ड फॉइल क्यों यूज करते हैं और ये कॉलीमीटर क्या होता है.
On a gold foil. The scattered particles produce scintillations on the surrounding
अगेन
screen.
scintillations
The
means small
scintillations could be
sparkles
observed
और
through a
small
microscope,
twinkles.
which
देखो
could
वो
be moved
चमक
to
रहे हैं.
cover
You
different
can see
angles
this
with
this
respect to the
चमक्स.
incident beam. It was found that most alpha particles passed straight through the foil, while a few were deflected, that is, scattered, through various scattering angles. A typical scattering angle is shown by theta in the figure.
ये देखिए यहाँ
Only
पे
about
थीटा.
0.14% of the incident alpha
So all these things you
particles
don't have to
were
remember, rather you
scattered
don't
through
have to
angles
remember this
larger
entire
than
thing.
0.1
बट वो
degree.
एक्सपेरिमेंट कैसा था, सेटअप
Even
अच्छा
out
है
of
तो
these,
देख रहे हैं.
some were deflected through very small angles. About 1 alpha particle in 8000 were deflected through angle larger than 90 degree, and a fewer still were deflected through angles as large as 180 degree.
यस, डन. तो ये याद नहीं रखना.
Rutherford's atomic model.
ओके, सो ये सब याद नहीं रखना है.
ओके.
हाय ब्रो, कैसा है तू?
मैं तो अच्छा हूँ, तू बता तू कैसा है.
यार मैं तो ठीक हूँ. वैसे पढ़ाई कैसे चल रही है तेरी?
एकदम मस्त चल रही है.
क्या बात कर यार, मैं तो थक गया ढूंढते ढूंढते इंटरनेट पे. यूट्यूब पर भी देखा, पर मैथ्स के सम्स के सारे सॉल्यूशंस कहीं पर भी नहीं मिल रहे. इवन मॉम हेल्प मी, बट उनको भी नहीं मिला.
क्या बात कर रहा है, मेरा तो हो गया सब कुछ.
चल रे, पक्का मत मुझे कुछ भी. तूने पक्का डाइजेस्ट से कॉपी किया होगा. वो तो मैं भी कर सकता था, बट स्टेप समझना भी तो इम्पोर्टेंट है ना यार.
डाइजेस्ट वो तो मैंने लिया ही नहीं है. पापा ने बस होम रिवाइज का पूरा सब्सक्रिप्शन ले लिया है. होम रिवाइज पे अलजेब्रा, ज्योमेट्री, इन सब के सारे सम्स के सारे सॉल्यूशन एक ही जगह पे होते हैं.
वाह यार, मतलब सब कुछ एक ही जगह मिल जाएगा.
और नहीं तो क्या. तू भी ये ऑनलाइन सर्चिंग छोड़, क्योंकि ऑनलाइन सर्चिंग में तुझे 2 या 3 ही सम्स मिलेंगे. लेकिन अगर तुझे तेरे सारे सम्स के एक्सप्लेनेशन चाहिए तो तू भी होम रिवाइज ले ले. बाकी होम रिवाइज सब संभाल लेगा.
होम रिवाइज, अब सर्चिंग बंद और लर्निंग शुरू.
ये है संजू की माँ और ये है राजू की माँ.
संजू, बहुत हो गया खेलना, अब थोड़ी पढ़ाई भी करो.
राजू, बस हो गई पढ़ाई, अब थोड़ा खेलने भी जाओ.
पता नहीं ये छाया राजू को कैसे पढ़ाती है कि वो पढ़ाई से हटने का नाम ही नहीं लेता.
अब बनाएं अपने बच्चे की पढ़ाई को उनकी गेम की तरह इंटरेस्टिंग होम रिवाइज के साथ, जिसमें टेक्स्ट बुक का हर सेंटेंस बच्चे लैपटॉप या टीवी पर एनिमेटेड मूवी की तरह देखकर एंजॉय कर सकते हैं. होम रिवाइज, जो बनाए हर सब्जेक्ट को इतना इंटरेस्टिंग कि आपको कहना पड़े.
बस हो गई पढ़ाई, अब थोड़ा खेलने भी जाओ.
होम रिवाइज, अब पढ़ाई हुई आसान.
Okay, let's go. Right? So now we'll be looking in Rutherford's atomic model, right? Okay.
Model. Results of Gelger-Marsden experiment.
So right, there was an experiment done by his colleagues. He also had Thomson's model. So he had some base to learn from and to act upon. So he decided, to do his own experiments. Again, he used the same gold foil. Okay, so गोल्ड फॉइल पे एक्सपेरिमेंट करने के बाद उसको पता चला, सेम एक्सपेरिमेंटल सेटअप, थोड़ा चेंजेस लाया उसने, बेसिक चेंजेस, तो उसको 3-4 चीजें पता चली, राइट? ही लर्नड अ फ्यू 3-4 थिंग्स दैट वर वेरी इसेंशियल फॉर नोइंग कि एक्चुअली चल क्या रहा है। ओके, द फर्स्ट थिंग इज, ये जो स्कैटरिंग आपको दिख रहा है, सी इन दिस एग्जांपल और दिस मॉडल, यहाँ पे आपको जो स्कैटरिंग दिख रहा है उसको भी सेम स्कैटरिंग दिखा, ओके, बट कुछ रेज ऑफ लाइट रिबाउंडेड, मतलब आगे गए, लग के वापस आए, यू नो, इट्स लाइक दिस कमिंग बैक दिस, मतलब उधर लग के रिटर्न आए। ओके, सो ही लर्न कि यार उधर कुछ ना कुछ तो एनर्जी होगा, कुछ ऐसा बड़ा पार्टिकल होगा, बड़ा एज इन ऑब्वियसली फॉर दैट स्मॉल वर्ल्ड अ ह्यूज पार्टिकल। ओके, सो कुछ बड़ा पार्टिकल होगा जिसको लग के मेरे रेज वापस आ रहे, तो एट द सेंटर ऑफ दैट एटम देयर मस्ट बी सम काइंड ऑफ big mass, okay, big mass which is leading to rebounding of the rays, ये फर्स्ट पॉइंट उसको पता चला। देन उसको स्कैटरिंग भी दिखा, राइट? तो बहुत सारे अल्फा पार्टिकल जो थे, जो हीलियम की बात हम कर रहे हैं, तो पॉजिटिव पार्टिकल्स या अल्फा पार्टिकल जो थे वो पास होते डायरेक्टली, राइट? मतलब कुछ रिबाउंड नहीं, कुछ स्कैटरिंग नहीं, कुछ डिफ्लेक्शन नहीं, कुछ नहीं, जा रहे सीधा, पॉजिटिवली चार्ज पार्टिकल सीधा 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 जा रहे, कोई अड़ाने के लिए है नहीं, तो देयर इज नो स्टॉपेज, देयर इज नो स्पीड ब्रेकर एज सच, तो दे आर रनिंग विद हाई स्पीड। ओके, सो ही लर्नड कि यार यस, अगर ये भाग रहे दौड़ रहे तो देयर इज सम एम्प्टी स्पेस एज वेल, completely empty space, no charge, no what do you say, a big particle or no other particle, कुछ उसको डिफ्लेक्शन करने के लिए कुछ नहीं। ओके, सो उसको पता चला, एम्प्टी स्पेस का पता चला। देन फ्यू ऑफ द रेज ऑफ लाइट वर डिफ्लेक्टेड एज वेल, राइट? दे वर डिफ्लेक्टेड। डिफ्लेक्शन meant यार it can be either due to the weight of the particles inside, or maybe it may be due to the charge of the rays and the charge of the particles inside. अगर अंदर के पार्टिकल्स का चार्ज बहुत ज्यादा होगा तो डिफ्लेक्ट करेंगे, तो रेज जरूर डिफ्लेक्ट करेंगे, बट अंदर के पार्टिकल का वेट ज्यादा होगा तो डिफ्लेक्शन कम होगा। तो ही अंडरस्टूड कि डिफ्लेक्शन है तो अपने पास एक ही सेंटर में एक बड़ा पार्टिकल है जिसकी वजह से रिबाउंड हो रहा है, राइट? तो रिबाउंड वो पार्टिकल की वजह से हो रहा है, तो देयर इज नो अदर पार्टिकल विच इज गोइंग टू कॉज सम काइंड ऑफ रिबाउंड। ओके, तो ही रियलाइज दैट ओके, एक पार्टिकल हमने साइड में रखा, तो जो स्कैटरिंग जो हो रहा है, दैट स्कैटरिंग इज बिकॉज ऑफ चार्ज पार्टिकल्स। So अपना alpha rays are positively charged, so there must be some kind of different charges inside which are causing that rays to deflect from their normal angle. Okay, so these were the three things. और वो जो center mass वाला particle जो उसको मिला था, उसको उसने नाम nucleus दी थे. So he was the father of nucleus. You can say he was the one who discovered the nucleus.
Experiment could not be
Now we can just
explained
go
by
through this.
Thomson's model. In that model, the positive charge was uniformly spread over the large sphere constituting the atom. The volume density of the positive charge would thus be very small, and all of the incident alpha particle would get deflected only through very small
See,
angles.
वॉल्यूम डेंसिटी मतलब क्या है कि इतना बड़ा एटम रहेगा, समझो ये इतना बड़ा एटम है, ये जो सर्कल दिख रहा है अभी आपके सामने फिलहाल, तो इतना बड़ा अगर वो एटम है, तो ये जो सारा है ना, इसके अंदर वो पॉजिटिवली चार्ज पार्टिकल स्प्रेड है। अभी बहुत बड़े कंटेनर में बहुत थोड़े थोड़े जगह पे अगर स्प्रेड होंगे तो उसका वॉल्यूम डेंसिटी हमेशा कम होगा। वॉल्यूम वॉल्यूम डेंसिटी कम होने की वजह से डिफ्लेक्शन भी है वो बहुत कम एंगल से हो रहा है। ओके,
Rutherford argued that the alpha particle which were deflected back must be encountered a massive
this is the
particle
first point
with
which I
large
said.
positive charge
ये
so
जो
that it
रिबाउंड
was
हो रहा है
repelled
या
back.
रिपेल्ड बैक हो रहा है।
From the fact that extremely small number of alpha particles turned back while most other passed through almost undeflected, he concluded that the positively charged particle in the atom must be very small in size and must contain most of the mass of the atom. From the experimental data, the size of the particle was found to be about 10 fm,
Femtometers.
that is femtometer 10 to the power minus 15, which is about 10 to the power minus 5 times the size of atom. The volume of the particle was thus found to be about 10 to the power minus 15 times that of an atom. He called these particles the
Nucleus.
nucleus
As
of an
I told you,
atom.
he's called the
He
father of
proposed that
nucleus.
the entire positive charge and most 99.9% of the mass of an atom is
Is concentrated to the
concentrated
center,
in the central
which he called
nucleus and
nucleus.
the electron revolve around it
ये
in
आपका
circular
इलेक्ट्रॉन
orbit,
रोटेट कर रहा है.
similar to the revolution of planet around the sun in the solar system. The revolution of electrons was necessary as within the electrons would fall into positively charged nucleus and the atom would collapse.
देखो अभी वो इलेक्ट्रॉन आपका रोटेट कर रहा है, राइट. एक कुछ तो एनर्जी उसके पास होगी जिसके तहत वो रोटेट कर रहा है. अगर एनर्जी है और उसको गोल घूम रहा है, इफ इट इज रोटेटिंग, तो इट्स ऑब्वियस दैट एट सम पॉइंट ऑफ टाइम इट इज गोइंग टू एक्सपेंड ऑल इट्स एनर्जी एंड देन फॉल इनटू द सेंटर. Okay, but it's not expending its energy, it's not completely losing its energy. Okay, तो ये भी बात है, उसका एनर्जी कहाँ से आ रहा है, एनर्जी खत्म क्यों नहीं हो रहा है. ओके, तो these were the few shortcomings or these were the few difficulties of Rutherford's experiment. Done.
The space between the orbits of the electron, which decides the size of the atom, and the nucleus is mostly empty. Thus, most alpha particles pass through this empty space undeflected, and very few which are in direct line with the tiny nucleus or are extremely close to it gets repelled and gets deflected through large angles. This model also explains why no positively charged particles are emitted by atoms while negatively charged electrons are. This is because of the large mass of the nucleus which does not get affected when force is applied on the atom.
Right, so this is what we had learnt already. Now we can go for atomic
Difficulties with
So
Rutherford model.
the difficulties or the shortcomings, as you can say, regarding Rutherford's model. Okay.
Though this model in its basic form is still accepted, it faced certain difficulties. We know from Maxwell equation that an accelerated charge emits electromagnetic radiation. An electron in Rutherford's model moves uniformly along a circular orbit around the nucleus. Even though the magnitude of its velocity is constant, its direction changes continuously, and so the motion is an accelerated
Accelerated
motion.
motion. देखो ना, continuous
Thus, the
motion में
electron should emit electromagnetic radiation continuously. Also, as it emits radiation, its energy would decrease and consequently the radius of its orbit would decrease continuously. It would then spiral into the nucleus, causing the atom to collapse and lose its atomic properties. As the electron
बट
loses
ऐसा होता है कि देखो ना, ये रोटेट कर रहा है, ये रोटेट कर रहा है, और इट कीप्स और इट स्टेज इनटू इट्स ऑर्बिट और इट कंटिन्यूज टू बी इन इट्स ऑर्बिट. मतलब उसको कंटिन्यूस फ्यूलिंग ऑफ एनर्जी कहीं ना कहीं से तो होता ही होगा. ठीक है, द इलेक्ट्रॉन इज गेटिंग सम एनर्जी फ्रॉम समवेयर एंड इट्स कंटिन्यूसली, तो ये एनर्जी एक्सपेंड करके कोलैप्स होकर अंदर गिर जाता, बट ऐसा होता नहीं, दे कीप ऑन मूविंग. तो ये शॉर्टकमिंग है, ये अपना रुदरफोर्ड भाई कभी बता ही नहीं पाए. He was unable to explain why this electron does not fall into this and keeps moving into its fixed orbit. Okay.
energy, its velocity changes continuously and the frequency of the radiation emitted would also change continuously as it moves towards the nucleus. None of these things are observed. Firstly, most atoms are very stable, and secondly, they do not constantly emit electromagnetic radiation and definitely not of varying frequency.
Right, so most atoms are stable, right. तो वो आपका जो एटम है उसके अंदर जो इलेक्ट्रॉन्स, एज वी लर्नड, वैलेंस इलेक्ट्रॉन्स, ये सारे इलेक्ट्रॉन्स तो वैलेंस ही होती है. एक स्टेबल एटमिक स्ट्रक्चर होता है. तो एटमिक स्ट्रक्चर देखेंगे तो मोस्ट ऑफ द पार्टिकल्स, मोस्ट ऑफ द एटम्स वांट स्टेबिलिटी, एंड इफ दे आर स्टेबल तो उनका इलेक्ट्रॉन्स कंटिन्यूस अपना जगह पे रहता है, दे आर इनटू देयर ऑर्बिट. ठीक है, दे डू नॉट कोलैप्स. बट ये वो एक्सप्लेन नहीं कर पाया. एंड अगर वो घूम रहा है, अगर रेडियस में अपना इलेक्ट्रॉन, इफ इट इज रोटेटिंग, इट इज गोइंग टू एमिट सम काइंड ऑफ एनर्जी दैट इज इन द फॉर्म ऑफ इलेक्ट्रोमैग्नेटिक रेडिएशन. And so but it is not emitting that kind of electromagnetic radiation, and this was again not
The
explained
atoms
by
have to give
Rutherford.
energy, example by heating, for them to be able to emit radiation, and even then they emit electromagnetic radiation of particular frequencies as will be seen in the next section.
Okay.
Rutherford's model failed on all these counts.
तो ये 2-3 पॉइंट, ऑल दीज काउंट्स एज इन 2-3 पॉइंट्स में बेचारा फेल हो गया. बट
Atomic
अगेन ही वाज द
spectra.
वन हु हेल्प्ड अस अंडरस्टैंड व्हाट इज a nucleus, what it is made up of and how it is working. उसके अंदर उसका पूरा चार्ज होता है, उसके अंदर उसका पूरा वेट होता है. ओके, ही वाज एबल टू एक्सप्लेन दैट, ही वाज एबल टू एक्सप्लेन व्हाई द डिफ्लेक्शंस आर हैपनिंग, व्हिच वाज डाल्टन्स एंड थॉमसन्स शॉर्टकमिंग. ओके, तो ये दो तीन लोग का जो शॉर्टकमिंग्स था उसके ऊपर इसने जरूर इंप्रूवमेंट दिया. यस, ही आल्सो हैड शॉर्टकमिंग्स and these were addressed later by Niels Bohr. Okay, so now we'll learn what is atomic spectra. Basically we have already seen the atomic spectra. Okay, we have already seen the atomic spectra. That is your इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम. उसी के तहत उसी के जैसा अपने को ये देखना है. तो as we had seen in the last chapter, when a metal is heated it gives out what electromagnetic radiations. हमने पिछले चैप्टर में पढ़ा था, first experiment that we done in the previous chapter. Okay, तो that radiation that is coming out from the metal, ठीक है, उसको हीट करने के बाद जो electromagnetic radiations निकल रहे हैं, those electromagnetic radiations are passed through a prism. राइट, जबरदस्ती से हम वो रेडिएशंस को प्रिज्म में से पास करते हैं. ठीक है, तो सब जो है आपके क्या बोलते हैं उसको, रेडिएशन जो है, जो सारे रेडिएशंस है सब पास होने चाहिए थे. राइट, एवरी रेडिएशन दैट वेंट इनसाइड द प्रिज्म शुड हैव पास्ड, बट दिस डिडंट हैपन. सारे पास नहीं हुए, तो सिर्फ थोड़े से ही पास हुए रेडिएशंस. एंड व्हाट वाज द रीजन फॉर इट एंड व्हाट लेड टू दिस is helping us understand what is atomic spectra. Okay,
We know that when a metallic object
See,
is
now this
heated,
is our
it
experiment.
emits radiation of different wavelengths.
तो ये सारे
When this
अलग अलग
radiation is passed through a prism, we get a continuous spectrum.
continuous
However,
spectrum
the
of
case
light.
is different when we heat hydrogen
Hydrogen
gas
gas.
inside a glass tube to a high temperature. The emitted radiation has only a few selected wavelengths, and when passed through a prism, we get what is called a line spectrum, as shown for the
ये
visible.
देखो लाइन स्पेक्ट्रम, अभी वो ये एक माइक्रो सेकेंड के डिफरेंस में देखो.
We get what is called a line.
यस, तो यू कैन सी दिस लाइन स्पेक्ट्रम. ये जो बीच का जो एम्प्टी स्पेस है, यहां से आपको रेडिएशन पास होते हुए मिले ही नहीं. ठीक है, रेडिएशंस वरंट पासिंग थ्रू दिस. तो ये ऊपर के मिले, ये नीचे के मिले, बीच का मिला नहीं. ठीक है, इट वाज इन द केस ऑफ हाइड्रोजन गैस. ओके, इट वाज इन द केस ऑफ हाइड्रोजन
spectrum
गैस.
as shown for the visible range. It shows that
तो
hydrogen emits
इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम
radiation
आपको
of
पता है,
wavelength
एक्स-रेज, यूवी
410,
रेज,
434,
Visible.
486 and 656 nanometer and does not emit any radiation with wavelength in between these
ये
wavelengths.
बीच में का
The
कुछ
lines
भी नहीं
seen
आता
in
है.
the spectrum are called emission lines. Hydrogen atom also emits radiation at some other values of wavelength in the ultraviolet, that is UV, the infrared IR, and at longer wavelengths. The spectral lines can be divided into groups known as series with name of the scientist who
Scientists
studied
who
them.
studied them or discovered
The
them, you can
series
say.
starting from shorter wavelengths and going to larger
Larger
wavelengths are called Lyman series,
Lyman,
Balmer series,
Balmer,
Paschen series, bracket
Paschen,
series,
bracket,
P-Fund series,
P-Fund
etc.
series.
In
So these were the people who studied these wavelengths कि भाई ये वेवलेंथ ही क्यों पास हो रही है, ये वेवलेंथ वाली रेडिएशन ही क्यों पास हो रही है. या इट वाज लाइमन जिसने शॉर्टर वेवलेंथ्स के बारे में पढ़ाई की. द अर्लियर वेवलेंथ हमने 456 के बारे में देखा, तो 456 रेंज में इसने पढ़ाई की कि यही क्यों पास हो रही है, इसके पहले के क्यों पास नहीं होते. फिर बाल्मर ने पढ़ाई की, देन इट वाज शॉर्टर टू लार्जर वेवलेंथ्स तक. इन सब ने दे ट्राई टू स्टडी इट एंड लर्न इट हाउ व्हाई एंड हाउ दिस इज हैपनिंग. ओके,
each series, the separation between the successive line decreases as we go towards the shorter wavelength and they reach a limiting value. Schematic diagram for this first
so
three
this
series.
diagram आपको if they ask electromagnetic spectra, तो आपको इसके पहले का जो डायग्राम था about the initial experiment of hydrogen, जो आपका 456 और 456 से लेके 656 तक जो था, वो डायग्राम आपको सिर्फ निकालना है. ये लाइमन लिमिट, बाल्मर लिमिट, पैशन लिमिट, ये सब अपने को सीरीज के बारे में नहीं बना. दे वोंट इंडिविजुअली आस्क टेल अस अबाउट लाइमन और बाल्मर. ओके, so you can
Are shown
just
in
learn
figure.
and not
The
try to
limiting
remember
value of wavelength
for a
for
long
each
term.
series is shown by dotted lines in the figure. The observed wavelength of the emission lines are found to obey the relation
So
1
this is
by
the relation,
lambda
1 by
is
lambda, that is
equals to
length,
r
that is
into
wavelength,
1 by
length
n
both.
square minus 1 by m
N
square.
minus m.
Here lambda is the wavelength of line, r is a constant, and n
N
and
m
m
are
are
integers.
integrals. N is equals to 1, 2, 3 and so
M will
on,
always be one number
respectively.
greater than, right? Always remember m जो है will always be one number greater than n. मतलब ये 2 3 से चालू होगा.
For Lyman-Balmer partial series, while m takes all integral values greater than n for that series.
कम से
The
कम एक
wavelength
नंबर.
decreases with increase in m.
सपोज हम लाइमन ले रहे, तो लाइमन में बेसिक n का वैल्यू 1 है, तो m का वैल्यू 2 से चालू होगा, राइट? इफ यू आर टेकिंग बाल्मर सीरीज, ओके, तो बाल्मर में n का इनिशियल वैल्यू 2 है, तो हम बाल्मर में m का वैल्यू 3 लेंगे. एंड इफ इन पैशन द वैल्यू ऑफ n is 3, तो हम पैशन में m का वैल्यू 4 से चालू करेंगे, राइट? सो दिस इज हाउ इट कीप्स इंक्रीज. ओके, so the wavelength decreases with the increase in m. तो obviously m जितना बड़ा होगा तो आपको shorter wavelength में आपको अच्छे से दिखाई देगा, but जितना जितना wavelength बढ़ता जाएगा, मतलब जितना जितना m बढ़ता जाएगा उतना उतना आपका ये कम होता है. इसका वैल्यू जितना ज्यादा बढ़ेगा, नेचुरली ये कम है तो नेगेटिव में जाने वाला है, तो वेवलेंथ विल ऑलवेज डिक्रीज, क्योंकि ये वेवलेंथ का फॉर्मूला है. देखो, वेवलेंथ इज इक्वल टू 1 अपॉन n माइनस 1 अपॉन m पकड़ो फिलहाल. तो अगर m ग्रेटर होगा, n से हमेशा ही ग्रेटर होता है, ठीक है, m इज ऑलवेज ग्रेटर. ओके, बट वो कितना ग्रेटर होता है वो मैटर करता है. तो m इज ऑलवेज ग्रेटर देन n, एंड दिस हेल्प्स अस अंडरस्टैंड द वेरियस सीरीजेस. ओके,
The difference in wavelength of successive lines in each series fixed value of n can be calculated from equation 15.1
this is the only
and
important
shown to
equation.
decrease with increase in m. Thus, the successive lines in a given series come closer and closer and ultimately reaches the value of lambda is equals to n square by r. In the limit
Where
m
m is
tends to infinity.
देखो,
for
m जब
different
इंफिनिटी आएगा, m जब इंफिनिटी आएगा तो 1 अपॉन इंफिनिटी हमेशा जीरो होता है, राइट? 1 अपॉन इंफिनिटी जीरो, तो 1 बाय m स्क्वायर निकल जाता है. अर्लियर इक्वेशन, ट्राई टू रिकॉल अर्लियर इक्वेशन. तो 1 बाय m जीरो हो जाता है, तो डायरेक्टली 1 अपॉन लैम्बडा इज इक्वल टू r बाय n स्क्वायर था, तो ये इनवर्स हो गया. आपका लैम्बडा ऊपर आ गया तो r नीचे और n स्क्वायर ऊपर हो गया, तो लैम्बडा का वैल्यू इधर से दिया होता है. ओनली इफ योर m इज इंफिनिटी.
different values of n. Atom of other elements also emit line spectra. The wavelength of the line emitted by each element are unique. So much so that we can identify the element from the wavelength of the spectral line that it emits.
Okay,
Rutherford's model could not explain the atomic spectra.
another shortcoming. So we have already learned 2-3 shortcomings or difficulties of Rutherford's model. You can add this third model, that third point, that Rutherford's model or his experiments could not help us explain the, what do you say, atomic spectra. ठीक है, ये आपका atomic spectra. Again, you don't have to draw this entire thing, you don't have to remember these things, these numbers. You'll absolutely go mad if you remember this. बहुत ज़्यादा हो जाएगा. ओके, जेई सीईटी में तो नहीं आता है, इसमें से क्वेश्चन एक्सपेक्टेड नहीं होता. तो या, we'll stop here for today, because then tomorrow we'll start with Bohr's atomic model, and that is the most lengthiest part in this chapter, entire chapter. तो उसी को टाइम लगेगा. उसके बाद एक बहुत छोटा सा पॉइंट, एंड देन द चैप्टर इज ऑलरेडी डन. ओके, सो इफ आई स्टार्ट इट टुडे, तो इट विल बी लाइक हाफ डन. तो 5 मिनट का एक्सप्लेनेशन में कोई पॉइंट नहीं बचेगा. सो विल कंटिन्यू दैट tomorrow. Okay, so I hope whomsoever has attended this lecture may come tomorrow prepared by revising this lecture or this YouTube video. Okay, till then, take care. We'll meet tomorrow same time, 4:30 to 6, and we'll try to finish this chapter. Okay, thank you very much.